Hi everyone, welcome to our discussion in Calculus 1. In this video, I will be discussing about limits and continuity. Let's proceed with the learning outcomes or the objectives. So at the end of the lesson, the learner or you will be able to illustrate the limit of a function using a table of values and a graph of the function. Distinguish between the limit of f of x as x approaches c and f of c. Illustrate the limit theorems and apply the limit theorems in evaluating the limit of algebraic functions, polynomial, rational, and radical. So let's start with the limit of the function and its definition. So consider a function of a single variable x. Consider a constant c, which the variable x will approach or get closer to. Take note, c may or may not be in the domain of the function. The limit, to be denoted by uppercase letter L, is the unique real value that f of x, the function, will approach as x approaches c. So in symbols, we write the process as the limit of the function f of x as x approaches c is equal to L. This is how you read it. Again, the limit of f of x as x approaches c is L or is equal to L. So if you recall, with our previous discussion, we have already talked about using the secant line in order to get the slope of the tangent line by looking for points that will get closer and closer to that certain value until such point they will be able to approximate and get the slope of the tangent line. So it's actually the same with this topic. So looking at a table of values. So this is the most common way to solve for the limit. So to illustrate, let us consider this example. So that's the limit of the function 1 plus 3x as x approaches 2. So here f of x, our function is 1 plus 3x, and the constant c which x will approach is 2. So x will get closer and closer to 2. To evaluate the given limit, we will make use of the table to help us keep track of the effect that the approach of x toward 2 will have on f of x. So, of course, on the number line, x may approach 2 in two ways, through values on its left and through the values on its right. So we first consider approaching 2 from its left or through values less than 2. So remember that the values to be chosen should be close to 2. Okay? So we start with values from the left side. So if we have a number line, I'm sorry. So if we have a number line right there, we're approaching, let's say this is 0, 1, 2, 3. So our goal is to get closer and closer to 2, both from the left and the right side. So if we start from the left side, we'll look for values close to 2. So here, going here. So we can actually use 1, since that's 1 unit before 2. We can use 1.4. 1.7, 1.9, 1.95, 1.997, 1.9999, and we can even use 1.999999. So you can actually choose any value as long as it's close to 2 from the left. Now, how do we get these values? We simply substitute these to our given function f of x. And we know that our function is given by 1 plus 3x. So using your calculators, you can substitute these to our function. And these are the values that we will be getting. So as we get closer and closer to 2 from the left, x is getting closer to this value. So now we consider approaching 2 from its right or through the values greater than 2 but close to 2. So this time, we'll be getting values from the right that's getting close to 2. So we have here 3, which is 1 unit from 2. We can have 2.5, 2.2, 2.1, 2.03, 2.09, 2.005, 2.000000001. As long as it's not 2 and it's close to 2, that's actually fine. And you can randomly choose any number. So substituting these values to our function or to the given function, you will be getting the following answers. Now, compare the value that we got as x approaches 2 from the right and from the left. So observe that as the values of x get closer and closer to 2, the values of f of x or the function get closer and closer to 7. So this behavior can be shown no matter what set of values or what direction is taken in approaching 2. So in symbols, our final answer is the limit of the function 1 plus 3x as x approaches 2 is equal to 7. Okay? I think that's very easy. Another example, let's investigate. So let's find the limit of x squared plus 1 as x approaches negative 1. So still be using the table of values. So by constructing the table of values here, c is equal to negative 1. F of x is equal to x squared plus 1. That is our function. So suppose it's our number line. This is 0. This is negative 1. That's negative 2. So it's from the left. That's from the right. So approaching negative 1 from the left, we can use the following: 1.5, 1.2. I'm sorry, negative 1.5, negative 1.2, negative 1.01, negative 1.001. Then substituting these values to our function, we will be getting the following answers. And observe what value that we got from the left. Now from the right side, approaching negative 1 from the right, that's right here, this side, we can use the values negative 0.5, negative 0.8, negative 0.99, negative 0.9999, and substituting those values to our function, these are the values that we got. So try to compare the value that we got as x approaches negative 1 from the right and from the left. So the tables show that as x approaches negative 1, f of x approaches 2. So in symbols, our final answer is the limit of f the limit of x squared plus 1 as x approaches negative 1 is 2. So now let's have this one. Investigate the limit of the absolute value of x as x approaches 0. So using still a table of values. So if this is our number line, it's 0 in the middle, it's 1 right there, negative 1 on the left side. So from the left, then from the right. So the values from the left, we can use negative 0.3, negative 0.1, negative 0.00009, negative 0.0000001, and substituting those values to our function. So we'll be getting the following answers. I hope you're familiar with the absolute value function. Like, let's say the absolute value of 3, that's 3. The absolute value of negative 3, that is still 3. So the answer, if you will get the absolute value of a certain number, will be the positive integer or the positive value. Now, from the right side, you can use the following values. 0.3, 0.01, 0.0009, 0.000001, and in the end, we will approach this number. So if you compare the values, we can conclude that hence the limit of the absolute value of x as x approaches 0 is 0. Next, we have another example. So let's investigate the limit of x squared minus 5x plus 4 over x minus 1 as x approaches 1. So by constructing table of values, wherein our c is 1, this is our function. Take note that 1 is not in the domain of f. Why? Because if we substitute 1 to our denominator, the denominator will become 0. And as we all know, if the denominator is 0, that will be undefined. So in evaluating a limit, remember that we only need to get very close to 1. We will not get to 1 itself. So that's fine. You can still solve for the limit. So from the left of 1, so we can choose, again, in choosing values in the table of values, it's random. You can choose any value as long as it's close to C. Then substituting those values to our function, we will get the following values. So that's from the left side. Now from the right, so we have 0.5, 0.88, 0.996, 0.9999. So again, it's your choice as to what values you will be using. Then substitute to the function, the given function. In substituting, in simplify, you can use your calculators in doing so. And in the end, we will arrive with this value and try to compare. So the tables show that as x approaches 1, f of x approaches negative 3. So in symbols, the limit of x squared minus 5x plus 4 over x minus 1 as x approaches 1 is equal to negative 3. Okay? So how about this one? Investigate through a table of values the limit of the function as x approaches 4 if we have a piecewise function. So f of x is equal to 1. F of x is equal to x plus 1 if x is less than 4. And x minus 4 squared plus 3 if x is greater than or equal to 4. Again, this is what we call, if you can still recall, this is a piecewise function. So this looks a bit different, but the logic and procedure are exactly the same. We still approach the constant 4 from the left and from the right. But note that we should evaluate the appropriate corresponding functional expression. So in this case, when x approaches 4 from the left, the values should be taken, or so the values taken should be substituted in x plus 1, since these are the values less than 4. So those are the values from the left. So indeed, this is the part of the function which accepts values less than 4. And so values close to 4 from the left. So again, it's your choice. You can choose any value. And we will end with this one. On the other hand, when x approaches 4 from the right, the values should be, or the values taken should be substituted in here, since these are the values that are equal, greater than, or equal to 4. So, values close to 4 from the right are the following. Substituting to our function, we will arrive with this answer. So observe that the values that f of x approaches are not equal. So namely, f of x approaches 5 from the left while it approaches 3 from the right. In such case, we say that the limit of the given function does not exist, or in symbols, you can simply write capital letters or uppercase letters D and E. So the limit of f of x as x approaches 4 does not exist. So as a remark, first one, we need to emphasize an important fact. We do not say that limit of f of x as x approaches 4 equals D and E. Nor do we write the limit of the function is equal to D and E, because D and E is not a value. So in the previous example, D and E indicated that the function moves in different directions as its variable approaches C from the left and from the right. So in other cases, the limit fails to exist because it is undefined. So such as for the limit of 1 over x as x approaches 0, which leads to division of 1 by 0. So again, in writing D and E, no need to write an equal sign. Just simply put the letters D and E beside the function. Remark number 2. So have you noticed a pattern in the way we have been investigating a limit? We have been specifying whether x will approach a value C from the left through values less than C, or from the right to values greater than C. So this direction may be specified in the limit notation. Limit of f of x as x approaches C by adding certain symbols. So if x approaches C from the left or through values less than C, then we write this one. Limit of f of x as x approaches C from the left. So notice the negative sign or negative symbol. Now, if x approaches C from the right or through values greater than C, we didn't write this one. We then write this one. So limit of f of x as x approaches C from the right. So notice the positive sign or the positive symbol. So furthermore, we say that the limit of the function f of x as x approaches C is equal to L if and only if limit of f of x is equal, the limit of f of x as x approaches C from the left and limit of f of x as x approaches C from the right is equal to L. So in other words, for a limit to exist, okay, for a limit to exist, the limits from the left and from the right must both exist and be equal to L. So therefore, the limit does not exist if the limits from the left and from the right side are not equal. So these limits, this one from the left and from the right, those are called one-sided limits, since you only consider values on one side of C. So thus we may say so in the first example, so the first example earlier, our limit was 7, since both from the left and from the right side, we got a limit of 7. So now let's proceed to determining the limit given the graph. And actually, it's very easy to identify the limit using graphs. So here, this is the graph of the, I'm sorry. Here. So the function is given by x squared plus 1. Now, as x approaches -1, so the value of f of x of the function approaches 2. So for example, number 2, this is the absolute value function. So as x or the function approaches 0, here, as x approaches 0, the limit is also 0. So again, it's very evident in graphs. Now here, this is another example we had earlier. So as the function approaches 1, our limit here is -3. Now recall for the piecewise function earlier. So as x approaches 4 from the left, the limit is 5. As x approaches 4 from the right, the limit is 3. So therefore, since the limits are not the same, we can say that the limit does not exist. So in general, if we have a graph of a function, such as below, it's actually easier to determine the limit. So let's have letter A. The limit of the function as x approaches -2. So we have -2 right here. The limit is 1. So the limit of f of x as x approaches 0 here. As x approaches 0, the limit is 3. Now for the third one, the limit of the function as x approaches 3 does not exist. Why? As x approaches 3 from the left, the limit is 0. From the right, the limit is 4. So we have different limits. Therefore, the limit does not exist. So I will be uploading this module or this handout in the Google Classroom. You can check some solved examples over here. But if you have questions, if you have clarifications, feel free to comment on the comment section below, or you can send a question in our group chat. Thank you so much for your time and for listening. You take care always. Bye-bye for now.